Hello guys, today I'm gonna explain IPv6, what is it, why it exists, and then we're gonna build a working IPv6 network in Proxmox so you can see it running. This video already assumes you know IPv4. If you don't, watch an IPv4 video first and come back. Let's do a quick recap on why IPv6 exists in the first place. So IPv4 has a 32-bit addresses, so that's about 4 billion. And they ran out. The fix was net. Your router pretends to be every device on your LAN, rewrites the source address on outgoing packets, and keeps a table so replies come back to the right device. It works. It's also why nothing on the internet can reach your machine unless you set up port forwarding. P2P often relies on stun and UDP hole punching, but that can fail under symmetric NAT. VoIP and multiplayer games handle this with fallbacks such as turn, media relays, dedicated servers, port forwarding, OPNP, NetPMP. That's actually the problem IPv6 solves. Not more addresses, direct addressing. On the image here you can see multiple devices on your home network that's protected by a router. In this case I'm assuming the router is also a firewall, has a firewall built in. So basically, if someone tries to reach your PC from the outside, they cannot, because to reach your PC, it has to go through the router, meaning it connects to your public IP address. And it says here, and I've explained it, it's one public IP for all these devices on this network. So basically, in contrast to the other setup with IPv4, here every device has its own public address, so there is no NAT and no translation, and the addresses are obviously bigger. So basically, IPv6, what does IPv6 change? So IPv6 has a 128-bit addresses, enough that every device gets its own public one. There's no NAT. Firewalls still exist. They still decide what gets through. That job doesn't change. What changes is the addressing model. Devices can talk to each other directly again. Basically, the address looks like this: 128 bits written as 8 groups, 4 hex digits, and columns between them. There's 2 shortening rules. One of those is drop leading zeros in each group. So 0 db8 becomes db8, and 0 0 0 0 becomes only 0. And rule 2 is collapse and run of all zeros groups. This is only applied once per address, otherwise would be ambiguous. So basically 0 0 0 0 colon 0 0 0 0 becomes colon colon. And the result of this full form IPv6 address, it's like this. So basically the 0 disappears here, and this trail of zeros becomes colon colon. This 0 also disappears from here. Basically every IPv6 address is 2 halves. First 64 bits are network prefix. Your ISP gives you this normally with some nuances. I'll get to those later. Every device on your same LAN shares it. This is true. Last 64 bits are an interface ID. The device picks this itself, random or derived from the MAC address of the device. Modern operating systems keep 2 at once, one stable and one that rotates for privacy. That 64-bit split is a hard rule, there's no reason for that. Because this is a hard rule, it provides SLAAC with the opportunity to work. If this was not a hard rule, SLAAC would not work. I will explain later what SLAAC even is. So basically, let's look at prefix sizes. So how prefixes get handed out. So regional registries give ISPs /32 normally. That's about 4 billion /64 networks. Your ISP gives you a /56 typically, and sometimes in rare cases a /48. So basically, if you already know IPv4, maybe you understand this. So if this is a /56, that means the first 56 bits of the address already locked, so they cannot be changed. And then the remaining, in this case 8 bits, can be changed. So you have 2 to the power of 8, meaning 256/64 networks. If in this case your ISP would allocate a /48, you would have 2 to the power of 16. That means 65,000 and something. And each /64 has more addresses than the entire IPv4 network. So basically it's a huge address space. You will not have to worry about running out of addresses. In IPv4 you conserve addresses. In IPv6 you spend them on segmentation. A guest network, IoT network, main LAN, each one gets its own /64. There's no cost. Now we're going to look at SLAAC, meaning stateless address auto configuration. This is how devices get an address without a DHCP server, like in IPv4. I mean, you can have a DHCP server of version 6 that normally doesn't happen with most setups, and I will not be explaining that in this video. Basically, this is what happens. The client connects and sends a router solicitation, basically asking, is anyone here? Then the router receives this and replies with a router advertisement that contains the prefix for this network and the router's link local address. So basically, here is your prefix and I'm your gateway. Then the client combines the prefix that received from the router and then combines it with its own 64-bit interface ID that can be random or MAC derived. And then basically at the last step does a DAD, checks if nobody has it already to make sure there's no duplicate devices on the same LAN. Let's look now of the comparison between SLAAC and DHCP side by side. The client requests an address to the DHCP server, and then the DHCP server replies, for example, 192.168.1.42, and then gives it a lease time. In this case, I'm not sure, I think the default is 24 hours, and keeps it organized. So basically the server keeps state, you configure the pool on the server. What happens with IPv6 with SLAAC? It's not the same, so the router broadcasts the prefix to the client, as we saw on the other slide. So prefix is this, and it gives always a /64 LAN for the client's last 64 bits with some way or randomly or MAC derived, verifies uniqueness. That's what I was explaining with that. And then the client, if it all goes well, the client has an address ready. Router keeps no state, no pool to configure. So basically FC00::/7 is a range for private IP addresses in the IPv6 range. In practice, you use FD00::/8 plus 40 random digits, which gives you a /48 that you only use. It's basically the same idea as a 10.0.0.0/8. I don't know if I said duplicate 0, but this is basically the same concept. Why do you have this when the devices already have a global address? So basically, because your ISP, the prefix of your ISP can change if you change ISPs or if they give you another one randomly. And you might have services that require an IP if you use the global prefix in your ISP changes, like this. So basically it was this and then became this after ISP change or reboot. References break locally, and the ULA, meaning unique local addresses, it's yours and generated once, and stays exactly this. It's not routable outside, obviously, and the references inside keep working, and your services and devices can keep talking to one another even if the outside IP changes. Let's move on to the lab in question. So basically, we have 4 virtual machines in Proxmox. One is our fake ISP running Alpine Linux with Kia for DHCP v6, prefix delegation, and RADVD for router advertisements. This gives us something that behaves like a real ISP. I will not be explaining this in too much detail because, man, this is an ISP. So I don't think if you want to set up this on your own network, you will not be having this part, only this segment here. The other one is the router running OPNsense and acting also as a firewall. Basically, it asks the ISP for a prefix and then splits that prefix into 2 other LANs. This is only for demonstration purposes. So basically, we have here the 2 separate networks that the OPNsense creates. So basically, the fake ISP delegated /56. This segment here stays exactly the same always. Only changes if your ISP for some reason changes it. And then the router OPNsense chooses the prefix ID for each LAN. In this case, I put my trusted with the prefix ID of 1 and the IoT with the prefix ID of 2 here. Remember, this is my trusted client will have both will be running with SLAAC, and my trusted client will generate its IP from this range and the IoT from this range. And then to tie it up, 3 bridges unite this whole setup. VMBR1 is the WAN link between the ISP and the router. VMBR2 it's the trusted LAN, and VMBR3 is the IoT LAN. All 3 bridges have no physical ports attached, so nothing leaks to my real network. Basically, this is an isolated setup. I don't have any network connection. So moving on to the Proxmox setup, basically here we have the 4 machines running that I talked about, the OPNsense router, the client one that's running on trusted, the Alpine ISP, and the other client that's running on IoT. So let's verify the stuff we have here. So basically on my node in system network, we have here the bridges that I created. So the ones that we talked about, this is my network bridge directly to my PC. This one has internet access. So we created another ones. So one lab. So one lab LAN. This is the trusted in the IoT. So VMBR1, VMBR2, VMBR3. So let's check each VM's network. So here OPNsense hardware, it has access to all 3, obviously. This is the router that will manage the packets between the 3 networks. So it has to have access to all 3. WAN, trusted, IoT. Then the client 1 has access to trusted. So here we can see it here. So trusted. VMBR2. The ISP has internet access, but it does not transfer it to OPNsense. So the rest of the network is isolated. And the other client has access to the IoT. So basically, let's open the ISP and check what's here. So basically, let me log in. Let me check. Okay. So basically, let's see the process that are running and confirm that the program that will give our prefix is running on this device, and it is. So you can see here. Now let's look at the OPNsense. And so this is what happens. So OPNsense does not have an interface directly. So I'm going to go to one of the clients, in this case, the client one running on trusted, and open its interface like I've done here. So basically, let's look at the interfaces that we have here. So assignments, and here you can see each one. VTnet 0, it's the WAN. VTnet 1, it's the trusted. And VTnet 2, it's the IoT. LAN here, it's the same thing as trusted. So let's look now at detail on each interface. So let's open WAN, and basically IPv6 configuration type, I have DHCP v6. So basically it will request a prefix from the Alpine ISP. Here we have the configuration basically. So the prefix delegation size is 56. Yeah, that's basically it. The rest you can leave at default. On trusted, we have a static IPv4. This is already the default. I'm using this to access the OPNsense interface, so I need this. But what is in our interest, it's the IPv6 configuration type. So we have track legacy. So basically, you don't have to care much about here, but basically this takes the prefix from the WAN. So parent interface, it's the WAN, and then the prefix ID. The prefix ID will be attached to WAN. The WAN. So basically, I have my WAN address, and then the colon, and then 0023, and then I have my /64 address, and the interface ID, it's basically a static allocation in IPv4. So my router, this interface, will have the first 64 bits that are normally used on that LAN, and then we'll have the only one. So basically it will be the first address available. You will understand it better when I show you the addresses. They are coming out. So the IoT has the same stuff. So we'll have a 12, and then the 1 will be identified as the 1. So now I'm going to show you, this is all well and dandy. So to send the router advertisements on OPNsense, you have to configure them. So basically you just create a new entry, select their interface, and then you put unmanaged. So basically the device will configure its own /64 bits with SLAAC only. To show you here, terminal, I'm gonna open a terminal and show you the IPv6 address. So basically this is the ULA. So as you can see here, it's forever and valid. So yeah, you can refer to this machine particularly by this IP. So basically we have 3 other IPs. We care about these 2. So basically this is the temporary /privacy IP generated and temporary, as the name says it. And then this one is the one that will use mostly. Let's show on the other client the same thing basically. So let's confirm. So IP/6 address show. Wait, wrong keyboard layout. So here, as you can see, let's check it. As you can see here, we only have, so here I was wrong. The one that we'll be using it's this one. So these two. Yeah. So basically here we have the ULI as on the other machine, and then we have the temporary address and then the one we'll be using. I've configured in OPNsense Firewall to let all traffic between the VLANs, and then I'll change it to not let all the traffic through the VLANs and try to ping the other device. So I'm gonna make the requests from the trusted VLAN computer. So let's try this. So I'm gonna try to ping the device. This is going to work, hopefully. DB8. This is the ISP prefix along with this IA40, and then we have the prefix that we set on OPNsense for the IoT. This in this case 12. Let me check. I'm looking at my phone. And then 2D EC F772 E98E A041. So let's try. As you can see, the ping is going well and responding. So we're sending a ping from the trusted VLAN, from a trusted VLAN device to a trusted LAN device, sorry, to the IoT, and it's working fine. Now we're gonna try to change the rules on OPNsense to not let these two interfaces talk to one another. So let's try firewall rules. So we're making the request from LAN or trusted, and we're gonna make a new rule. We're gonna make a blocking rule from LAN, direction in, IPv6, protocol any, source. Let's do the source on LAN network, and I'm gonna do the destination on IoT network. And yeah, this should be fine. We're gonna apply the change. No, we have to give it priority. We're gonna apply the changes. And so basically we have a blocking rule on every IPv6 protocol. When the source is the LAN net and the destination is the IoT, basically. A device on the trusted LAN will make a request to the IoT. This request will be blocked on the firewall level. So we're going to try the same thing again. Now we're going to receive an error. So this is what we expected. So I'm trying to ping the IoT network from a device on trusted, and the ping is not going through. If I remove this rule and apply it swiftly, now we can ping the other device successfully. So this is my last slide. So a recap. So the ISP delegates a prefix, typically a /56. So you have 256 different lanes you can use for different things, and isolate the devices between one another. Then the router requests to the ISP its prefix and then splits it into /64 networks, one per LAN. Each /64 gets a router advertisement broadcast on it. Then the devices will auto-configure via SLAAC. At last, the firewall still decides who passes through, as we saw in the demonstration. So no NAT, no port forwarding, no DHCP server, no address conservation.